Okay, so let's talk about backtracking and specifically backtracking in combination with recursive algorithms that use search trees. And let's talk about it through example. Namely, let's have an example. Let's consider the NQueens problem as our sort of vehicle to discuss backtracking. Okay, so what is the NQueens problem? Well, the idea is you're given a chessboard here, and you want to know how many queens could you place on one board. Okay, so you have a chessboard and you have a bunch of other queens. Okay, queen, 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 and you want to know, could I place a queen here? Yep. Could I place a queen here? Yep. Could I place a queen here? Nope. Could I place it here? Nope. Oh, yes. And then could we place another queen like so? Oops. Can't place it here, but we could place it there. And could we place another queen? Oops. Can't place it there. Oh, and we couldn't place, oh, my apologies. We couldn't place that queen there. Oh, I know a lot of you are yelling through your screens. We couldn't place that queen there, but we could place a queen here. All right? So, the idea behind the n-queens problem is, can we place, how many queens could we place on a normal 8x8 chessboard? And could we place 8 queens on this chessboard? And what are their configurations? That is the queen's problem. Okay, nice little chess problem. So let's start off, and maybe one way to solve this problem is just blind luck, right? Let's just see if we could get a configuration right off the bat that works. So we started off with a chessboard, a queen on it, and one thing we realized very quickly is that wherever we place the queen, for instance, since we placed the queen here, we've closed off a bunch of other squares that queens could have gone on. Okay, so for every queen that we place, it basically closes off a bunch of squares for subsequent queens. Okay, that's the magic of this problem. That every time you do one queen, you're basically limiting your options more and more and more. So we could place another queen outside of the first queen's range, and that queen blocks off more squares, right? Then we place the third queen outside of the range of the first two queens. And now we got a whole bunch more squares that are closed off. And we place a fourth queen and we place a fifth queen. And doing sort of a intelligent analysis, we could see that now we can't place any more queens because every square is guarded by one of the 6 previous queens. Okay, so we didn't quite get to 8. We got to 6. So good news is we know we could place 6 queens on the chessboard. Bad news is we're still not sure if we could place 8 or not. I mean, we know that this didn't work out, but that doesn't mean that there's not some other configuration where 8 queens would fit on a chessboard. So, what do we do? What do we do? Well, well, we look on Google Scholar. We look on Google Scholar and see that the problem was originally published in 1848 and it was solved in 1850. And the solution is a single image here. The solution is just that. You could place 8 queens on the chessboard where um, where each queen is not guarding each other. And the intuition out here is kind of cool, right? The intuition is that queens can move in a horizontal and diagonally, but they can't move um, according to the knight's movement, right? So you just put a queen down, and then you place subsequent queens where the knights would have gone. Cool, huh? But how do we solve this problem for a general n? We know that the queen's problem for a 8 by 8 chessboard allows us to place 8 queens. What if the chessboard was 5 by 5? Could we place 5 queens on a 5 by 5 chessboard? What if the chessboard was 20 by 20? Could we place 20 queens on a 20 by 20 chessboard? Notice, well, let me hold that thought for a second. But how do we solve this problem for a general n? And that's the question. Well, there's one option, which is just to search all possible configuration of n queens on a n by n chessboard, and then see if any of the queens are guarding each other, right? So for instance, I could start off with Q, 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 and know that this is not a valid configuration, which isn't good. I could start off with Q, 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 Q1. See if that works. Nope, not a valid configuration. Maybe I need to move the last queen there. Maybe I need to move the last queen there. Still no, bam, still no. Then I would go down to the next queen, bam. Then the next queen, bam. Then we got to move these queens onto other squares. And keep trying, right? And then we basically brute force this problem. After we check all the possible permutations of queens on chessboards, and then we check if any queen can attack another queen on the chessboard, and if it can, it's not a good permutation. If they can't, then it is a good permutation, and then we just jot it down. Okay? So what's the problem with this? The problem with this is that it's going to be incredibly slow. Just shockingly slow. Even by a 5 by 5, we got to have, there's going to be roughly 5 choose 25, or no, sorry. There's going to be 25 choose 5 permutations, possibilities, sorry. Abilities. And then we got to check every time. We got to do O of n squared work to check if the possibility is valid. Okay? And this is just simply a huge number. Okay? This is a huge number. And this is only for a 5 by 5 board. This is only for a 5 by 5 board. So even if you have an amazing computer, even with our modern computers, we wouldn't be able to solve the problem like this through sheer brute force. Right? Now, maybe we could be a little smaller. So this search tree is obscene. This search tree is not going to happen. Okay, we're not going to search every single possible permutation of queens on a chessboard and then check. Not going to happen. But maybe we could be a little more intelligent. Why did I keep saying, can we fit n queens on a n by n chessboard? Why didn't I say, could we fit 13 queens on an 8 by 8 chessboard? Why not 24 queens on an 8 by 8 chessboard? Why did we limit ourselves to 8 queens on a 8 by 8 chessboard? Why did I limit myself to 5 queens on a 5 by 5 chessboard? And the answer is because we know that a queen, when we place it, it guards the entire row. So we can't put any more queens onto the chessboard than there are rows. Right? So in an 8 by 8 chessboard, that piece of logic alone tells us that there can't possibly be more than 8 queens on an 8 by 8 chessboard, because if we can do the ideal thing and place each queen on their own row, that limits us to 8. Okay, so that's our first insight, which is that we can have at most n queens for an n by n chessboard. Okay? The queens can't be on the same row, column, or diagonal. So, what's our next recognition? Well, if the queens can't be on the same row, then maybe a better way to search the space, the possible permutations of queens, is to put each queen on a different row and just search if you can move the queen along that row to get a valid permutation. So let's say we start off with a queen here. We're not going to bother ourselves and place any queens here. And we're not going to bother ourselves and place any queens here. We're just going to place a queen on a new row. And we're going to place it on a new space right there. And similarly, we're going to place, the next time around, we're going to place a new queen there. We're not going to place it on the same row, and we're going to move the column, we're going to move it over a bit. And so on, right? We're going to place a queen, we're going to try the queen there, doesn't work. We're going to try the queen there, doesn't work. We're going to try the queen there, doesn't work. We'll try the queen there, works, okay? Then the next row around, then the next row, we'll put a queen down here, doesn't work. We'll move the queen here, doesn't work. We'll move the queen here, doesn't work. We'll move the queen here, works. All right? So that's how we'll reduce the search space. We're not going to search through every possible permutation of queens on and by a chessboard. We're going to search through every permutation where each queen is on its individual row. That's how we'll do the algorithm. And so for a 5x5 row, it will be, the search space will be much smaller, right? This is the first queen. First queen on first row. And what this search tree is saying is that first we try to put it on row 1. On column 1. Okay, first we're going to start off with the queen right here. And then if we start off with the queen right here, maybe we'll try to place queen 2. I need to use a different pen. Or if we're going to try to start right here, maybe we'll place the second queen on the second row. At 3, at column 3. So first queen, first row, first queen, second queen, third column. There, that's pretty good. Or then we could try fourth column or fifth column, and then so on. The third queen we could place it on column 5, and so on. Then we could try different values for the queen on column 6, and so on. Okay, so doing things this way, doing the search space this way, leads us to several solutions that you could place 5 queens on a 5x5 chessboard. It also leads us to some solutions that, you know, if you have a configuration that's basically, let's draw it out. Actually, let's just do it here. 152. If we have a configuration that's 1, 5, 2, then we screwed up, right? Then we get to a space where we can't put any more queens down because each of these columns are covered by another queen. Each of these spaces. So this permutation does not work. Okay? These positions together do not work. And that's what this search tree shows. But some positions do work. Okay? So this is how we reduce the search space for the NQueens problem. We do a recursive search over an implicit tree, and we backtrack, quote unquote backtrack, if certain possibilities do not work. For instance, we backtrack, we do the recursive space here, and then if we go down a branch where we can't get to n, then we just return, we return, and then go down more permutations where we can. Okay, so this type of search actually will let us get all the permutations where 5 queens could coexist on a 5x5 chessboard. And this is the code for what we just did, i.e., we have a permutation, we have a array that stores the actual the current layout of the board with the current number of queens on it, and then we have what row we're on, and then we have what number of queens are, what the number of queens are. And so so the base case is if we exceed the number of rows, i.e. this is space 0. If the number of rows gets more, if the number of queens becomes the number of rows, then we print the board. We reach a valid permutation. But on the other hand, if we don't make this condition, then it means that we're still constructing our board. Okay, and if we're constructing our board, we just go through every possible column value. We know what row we're putting the queen on, and so we assign this column value to the row, and then we recursively call this function. And at the next step, it will analyze the board and tell us if this partial permutation is valid. If the partial permutation is valid, then we keep on going. If it's not, then we abandon ship and we go up the branch and go down. Okay, so NQueens problem. Very simple problem, simple solution, but its purpose is simply to demonstrate how we could use backtracking to go from some search tree that is frankly insane to a reasonable search tree that can be solved by a modern computer for reasonably large values. And speaking of reasonably large values of n, the Queen's problem, since it's been published, it is one of those mathy problems that mathematicians love to work on. You know, number theory is every mathematician loves number theory. Every mathematician loves sequences, and the NQueens problem yields some interesting sequences. Okay, and so if you look at the number of solutions, the number of possible solutions to each to the NQueens problem, as n increases, you will notice that the number of solutions increases. I mean, this isn't necessarily exponential. I don't know really what function would describe the sequence, but it does increase greatly as n increases. And in fact, for larger values of n, computation becomes very difficult, and you would need like supercomputers and stuff to solve them. And I'm not sure if anyone has invested those types of resources to get to n equals 30, 40, 50. Okay, so that's the NQueens problem. That's what backtracking is. I know it seems silly because backtracking is something a lot of computer scientists and a lot of you guys, computer programmers, or computer scientists, you are computer scientists, a lot of you guys would do naturally, right? This isn't the hardest computer science topic you've ever dealt with. You would probably do this naturally, but even though it is something that you would do naturally, it is a technique that we should name. And the idea of pruning our search tree is simply named backtracking, and that's all it is. Okay, so whenever you hear backtracking, remember just reducing the search tree. All right.